Hello and welcome. This week we are transitioning from our discussion of descriptive statistics and probability distributions into building the foundations of statistical inference. In this lecture, we're going to talk about the means of samples as well as the distribution of sample means, and we're going to introduce a really key concept called the central limit theorem. Let's get started with an example. We're going to start our discussion by looking at a relatively recent survey from the Pew Research Center, which was looking at public opinion about the Iran nuclear deal shortly before Congress voted on that deal. As of September 2015, about 21% of people approved of the agreement, about 49% expressed disapproval with the agreement, and about 30% of people said that they didn't know what they thought about it. So the study is making claims about public opinion in the entire United States about the Iran nuclear deal. How can this study make claims about an entire population from a survey of just a relatively small sample of people? Well, this is a question of statistical inference. How do we extrapolate from the data that we have to answer our research questions, and how can we be confident that our answers are right? Starting this week, we're going to be tackling those issues of statistical inference. Before we get into the meat of that question, let's go ahead and talk a little bit about the survey design for this particular study. So any good, well-conducted study is going to give you information about how they did the survey, what their sampling procedure was, and things like that. So here's some basic information about this survey about public opinion on the Iran nuclear deal. We find that the interviews were conducted for the sample of 1,004 adults, 18 years of age or older, living in the continental United States. 501 of them were interviewed on a landline, 503 were interviewed on a cell phone. And there are a couple more details of the survey methodology here if you would like to look at them. The main point here is that we're going from this sample of just over 1,000 adults and extrapolating to the United States adult population of more than 200 million people. So how can we do this, and how certain is the Pew Research Center about their estimates of how many people approve, disapprove, or don't have an opinion about the Iran nuclear deal? In this table, we're given a little bit more information about the sample sizes and some subsample sizes, as well as what's called the margin of error. Off to the right column here, we have 3 to 6 percentage points as the margin of error for claims about the total sample. So for example, the study claims that 21% of adults approve of the Iran nuclear deal. And we have this margin of error of 3 to 6 percentage points. So how do we interpret that? Well, we have 21% plus or minus the margin of error of 3.6%. That's a 95% confidence interval, which we're going to talk a little bit more about the meaning of in this lecture and the next lecture. But what this means is that with 95% confidence, between 17.4% and 24.6% of American adults approve of the Iran nuclear deal. So based on the survey data for this sample of American adults, the study's best estimate of the proportion of American adults who approve of the Iran nuclear deal is 21%. They also provide us this 95% confidence interval. This is sort of a range in which they're pretty darn sure that the actual proportion falls into. So between 17.4% and 24.6%, they're very confident that in that range is the actual proportion of American adults in the entire 200 million plus population who support this deal. In an earlier lecture, we talked about how in our research questions, we're interested in a broader population, but we usually are not able to get data on that whole population, and so we draw a sample. We're studying population parameters. Those are our objects of interest. Things like what the mean of the population is, what the shape of the population distribution is, what proportion of the population falls into different categories, and things like that. But we're not able to directly measure the population parameters in almost all circumstances. So what we do is we take a sample and we calculate what are called sample statistics, which are our estimates of the population parameters. Depending on the sample we take, those sample statistics are going to be different. If I take two different samples, those samples are going to be made up of different observations. They're going to look different from one another. The mean of one is going to be different from the mean of the other. Their standard deviations are going to be different. And one of those samples might have extreme outliers and the other sample doesn't, things like that. So sample statistics are going to vary from sample to sample because those samples look different from one another. We want to quantify how those sample statistics vary, how much they vary, how different samples are going to look from one another as we try to determine a margin of error around our point estimates. So this is what in the previous study was done to determine this margin of error around the point estimate of 21% approval of the Iran nuclear deal. The people who did this survey also did some studying about the variability of this distribution, the variability in the United States population, and came up with this estimate of the margin of error around their point. So we're going to be talking about how exactly we do this. How do we quantify the variability of our sample statistics? Before we do that, let's talk about a brief example. Imagine that you take a sample of 1,000 women from the United States population and you record their heights and you calculate the mean of that sample, so the average height for those 1,000 women that you sampled. So you record that mean and then you do the same experiment 9 more times with a different sample of 1,000 women. You record the average of those 1,000 heights until you have 10 sample means. Would you expect that these sample means are exactly the same across all 10 samples, that they're somewhat different, or that they're very different from one another? It would be extremely unlikely for all of those sample means to be exactly equal to one another, but they're probably also not going to be extremely different from one another. We're probably not going to accidentally randomly sample a whole bunch of women who are 6 feet tall and another random sample of women who are only 5 feet tall. Probably our random samples of 1,000 women are all going to have pretty much the population average height. Let's stick with our example of heights of women in the United States for another minute. Let's say that this distribution of heights is approximately normal with a mean of 64 inches and a standard deviation of 3 inches. If we didn't have this information about the underlying population, but we wanted to estimate the average height of women in the United States, we could take a sample and use the mean of the sample as our sample statistic to estimate the unknown population mean, the population parameter that we're interested in. We know that the sample statistic is going to be a pretty good estimate of the population mean because of something called the central limit theorem. The central limit theorem says that if you take a sufficiently large samples from a population, the means of those samples will be normally distributed, centered on the true population mean, regardless of the distribution of the original population. This is a really powerful concept in statistics. Let's go ahead and look at a couple of demonstrations to explore how this works, and then we're going to get a little bit more into the mathematics of the central limit theorem. So here we're looking at an applet to show us some stuff about the central limit theorem for means. So we were just talking about a distribution of heights with a mean of 64. This is a normal distribution, so I have that option clicked already. So let's say a mean of 64 and a pretty low standard deviation of 3. So we're going to have like a really tight normal distribution here centered on 64 with a standard deviation of 3. Now let's say that I want to take samples of size 100. So I'm going to sample 100 women from this distribution and record their heights. I'm going to do that over and over again, 200 times. So in the population, I know that my mean is 64. Here in the first sample, what I see is that I have a mean of 64.65. In the second sample, I've got a mean of 64.11, and so on. Here I'm going to record all of these means. And we're going to take those samples 200 times. And what we end up with is this new normal distribution. This might be a little hard to see because the distribution is so skinny. But in this distribution, our mean is 64. So the mean of this distribution of sample means, so the mean of means, is 64, which is exactly equal to the population mean. And this itself has a standard deviation, a standard error of 0.33. And we'll talk a little bit about how that standard error is computed in a little bit. What this demonstrates is that when we sample over and over and over again from this population, the distribution of the means of all of those samples is going to be normal. So a cool thing about the central limit theorem is that it doesn't matter what the underlying distribution is. The fact that the distribution of sample means will end up being normal is regardless of the shape of the distribution that those means are drawn from. So let's do an example by looking at a uniform distribution. So let's say that we have a uniform distribution with a lower bound of 0 and an upper bound of 10. And we're going to do the same exercise where we sample 100 individuals from this uniform distribution, and we're going to take 200 different samples from that distribution. So the mean of the uniform distribution is 5, and its standard deviation ends up being 3 also. In our first sample that we take, here we see a mean from the uniform distribution of 4.36. In our second sample, our mean is 5.14, and so on. The same principle that we were using when we were sampling from the distribution of heights. And we're going to take, again, 200 samples. And what we end up looking at is a distribution of the means of 200 random samples. Each of those samples has 100 observations. And this distribution here of means selected from uniform distributions is a pretty normal distribution of means. So this is an indicator that the central limit theorem holds even when we're not sampling from a normal distribution to begin with. We go from a distribution of any type, take a bunch of samples, record the means of those samples, and end up with a normal distribution of sample means. We can also look at the central limit theorem using R. So let's go ahead and open up an R script here. What I'm going to do is I'm going to generate some random data from a normal distribution that's going to represent this population of women's heights that we've been talking about. So I'm going to tell R that I'm going to create a normal distribution. It's going to have, let's say, 30 million women in it, and it's going to have a mean of 64 and a standard deviation of 3. I'm setting a seed here. This gives R a starting number for generating random data. It just makes this replicable. That's not really important for our purposes right now. So R is going to go ahead and generate those couple million observations for me, and it's done. That was pretty quick for 30 million observations. So let's go ahead and look at the mean of this data that I just generated here. So our mean is 64.00012, so that's really close to this mean of 64 that I told R that I wanted. And that's the mean of all of these 30 million observations that I just took. Now let's say that I want to take a sample from this distribution that I just created. So I'm going to call my sample sample. I'm going to use the command sample. I'm going to tell R that I want to sample from these 30 million observations that I just created, and I want to take a sample of size 100, like we have been doing. So I can take that sample, and then let's look at the mean of that sample. So the mean is 63.87-ish, so pretty close to 64. I can do this, I can just run this again, and R will take another random sample for me, and I can look at the mean of that sample, and it's a little bit different, 63.71 or so. Oops. I can take another one, and I'm going to get a mean of 64.089. If I do it again, I get a mean of 64.107. So you can see that these means are all pretty close to the mean of the population, which is right about 64, but they vary a little bit around the mean like we've been talking about. So what if I want to look at a whole bunch of those means at once? I'm going to create this vector called sample means. I'm going to tell R that I want to do something 200 times, And this is going to take a mean of a sample from women's heights of size 100. So 200 times, we're going to take a sample from the women height distribution. The sample is going to have 100 observations in it. I'm going to take the mean of that. This is just doing this procedure that I have been doing, except for I'm going to do it 200 times, and I'm going to store all of them in this object called sample means. All right. This is a mosaic function, by the way, so I need to load the mosaic package first. All right. And now R is going to know what do means. It's going to take those samples for me, and once it does, I'm going to make a histogram of all of those means. So I'm going to say that I want the histogram to come from my sample means data, and let's say that I want 10 breaks, 10 bins in my histogram. And there we go, there's my histogram of 200 sample means from different samples from this women's height distribution, and it looks pretty normal. And it's centered around the actual mean of 64, which is what we would expect. It ranges between about 63 and 65, and this is what the central limit theorem tells us, that when we take samples over and over and over again, when we take the means of each of those samples and look at their distribution, that distribution is going to be about normal, it's going to be centered on the real mean, and it's going to look a lot like what the mean of the population is. So if I take any given sample, because of the central limit theorem, I know that that sample is really likely to be close to the population mean. And that's the power of the central limit theorem, is that I can take a single sample and I can know that my population parameter that I'm interested in is going to look pretty similar to the sample statistic that I calculate. Even if I have a population of millions and millions and I only take a sample of 100, I can take that sample and look at its mean and have reasonable confidence that this sample statistic is really close to my population parameter. So that's cool. So what we've been looking at are called sampling distributions. So those are distributions of sample statistics that are calculated from repeated samples from a population. We could look at sampling distributions of all sorts of sample statistics. What we've been looking at in our examples are sampling distributions of sample means. So distributions of means that we calculate by taking lots of different samples from a population and taking the mean of each one, then looking at the distribution of those. And when we take the sampling distribution of sample means, those distributions end up being centered on the true population mean and distributed normally. So now we come to the mathematical definition for the central limit theorem, which says that x bar, the sample mean, is distributed normally with mean mu, the population mean, and a standard error equal to the standard deviation over the square root of n. So the standard error of the sampling distribution is equal to the standard deviation of the population divided by the square root of n, which is the size of the sample. So we approximate the standard deviation for the population with the standard deviation of our sample, right? We don't have access to the standard deviation of the whole population, or we wouldn't be bothering with this sampling procedure. So we just approximate it. We take our single sample and we calculate the standard deviation for that sample. We use that as an approximation of sigma, and then we divide that by the square root of n, so the square root of the size of the sample. So if we take samples of size 100, we would divide by the square root of 100. And that's the standard error. That's our parameter for this distribution of sample statistics. I'm not going to talk about the proof of why the standard error of the sampling distribution is equal to this, but the thing that you should know is that as n increases, as we take larger and larger samples, the standard error decreases. So the sampling distribution is going to be this skinnier and skinnier normal distribution if we take bigger and bigger samples. As the sample size increases, samples are going to give us more consistent sample means, and the variability in that distribution is going to be lower, so the distribution is going to be tighter around the true population mean. This is why it matters to us to take big samples from the population. Bigger samples give us more consistent estimates, and we think that that's better overall. We do have to meet a couple of conditions to be able to use the central limit theorem. One really important one is independence. So the sample observations must be independent of one another. We talk about independence in some of our earlier lectures, so if you're unclear about that concept, you can revisit those, revisit the textbook readings on independence. Just means that when we take observations from the population, those observations don't depend on what previous observations were drawn. If we want to meet this condition of independence, we are more likely to do that if we take random samples, if we do random assignment in a trial, in an experiment that we're doing. And if we're sampling without replacement, we should sample less than 10% of the total population. This usually isn't a problem. We usually don't calculate samples anywhere near that big, but this is just a rule of thumb. The other condition that we need to take into account is the relationship between sample size and the skewness of a distribution. So remember, we can use the central limit theorem for any distribution. We can use it for a uniform distribution, a bimodal distribution, distributions with all sorts of skewness. But if the distribution is skewed, we're going to want a larger sample from that distribution in order for the central limit theorem to give us these consistent estimates of the mean. So for moderately skewed distributions, we want a sample size of at least 30. That's our usual rule of thumb. We can guess at the skewness of the population distribution by looking at the skewness of our sample, right? We assume that if we've got a good random sample, the sample is going to mirror the population. So we look at the skewness of our sample. If it's extremely skewed, we're going to want to take really big samples. If it's moderately skewed, we want to make sure that we're getting at least 30 observations. So that's been our lecture on sampling distributions and the central limit theorem. I've also posted a link to another video explaining the logic and the intuition behind the central limit theorem up on our course page, so I encourage you to check that out also. In our next lecture, we're going to be talking about confidence intervals, so I will see you then. Thanks for watching. Bye.